What's up, guys? Welcome to Calculus Club. In this video, I am going to explain the mathematical definition of the limit, also called the epsilon delta definition of the limit. All right, let's get into it. So the formal definition of the limit is as follows. The statement the limit as x approaches c of f of x equals L means that for each epsilon greater than 0, there exists a delta greater than 0, such that if this first statement is true, then this second statement will be true. Now, right now, this is a little bit complicated to just explain to you, all right? So what I'm gonna do is explain to you an analogy that's a little bit easier to understand, and then I'll come back to this definition and I'll explain all of the parts. Okay? So keep in mind this is a definition, meaning that if the limit exists and it equals L, then all of this will be true. If it's the case that the limit does not exist, well then you're going to be able to give an example such that all of this does not hold true. And if you can give that example, obviously the limit does not exist. Okay? So, first off, what I'm going to do is I'm going to replace the epsilon with this r sub y, which kind of represents the radius of y. Okay? So notice you have your L, you have r sub y plus r sub y and minus r sub y. You kind of have this radius y about L. All right? And I'm going to replace the delta with r sub x. Okay? So r sub x is, you guessed it, the radius about x, okay? So you have a plus r sub x and you have a minus r sub x. So I'm gonna get rid of this epsilon and delta and replace it with r sub y and r sub x to make it easier to understand, all right? So the next thing is I'm going to show this, imagine there's a debate going on, okay? You have two people, you have Mr. Green and you have Mr. Red, all right? So Mr. Green thinks the limit exists, while Mr. Red does not think the limit exists, okay? So the debate is going to go like this. So Mr. Green says, I am sure the limit exists. You can give me any radius of y you want, and I can always give you a radius of x, such that all x within r sub x of c, okay, which is this here, will correspond with y values that are within r sub y of L. Okay, a bit of a mouthful there, but let me explain it, all right? So the way this works is that Mr. Green says, Mr. Red, you can give me any r sub y you want, all right? So Mr. Red, the doubter, gives the r sub y, and Mr. Green says, I will always be able to give you an r sub x, such that all of the x values between c minus r sub x and c plus r sub x, all of these x values correspond with y values that are within the radius of y. If it's the case that I cannot give you an r sub x, then obviously, Mr. Red, you win the debate. The limit does not exist. All right? So what I'm going to do is I'm going to show you two examples. One example where the limit exists, where Mr. Green will win the debate, and then one example where the limit does not exist, where Mr. Red will win the debate. All right? So first off, let's talk about Mr. Green. Now, we already know that, well, what's the claim Mr. Green makes? Mr. Green says the limit as x approaches 4 of f of x, okay, this function is f of x, equals to negative 4. Now, we've already studied limits, so we know that, yeah, that's true, right? The limit does exist there, okay? So now Mr. Red is going to challenge this. So coming back, notice that our L is negative 4. Okay, so let me write here. L is negative 4. Okay, that's the claim. We claim the limit is negative 4. And our C is 4. Okay, so remember how this works. Mr. Green says, Mr. Red, you can give me any r sub y within negative 4. And I'll always give you an r sub x around 4 such that all of those x values will lie within that r sub y, okay? So let's make it easy at the beginning. Let's say that Mr. Red says, okay, I'm going to give you an r sub y equals to 1. Okay? So that means that we're going to be between -3 and -5, right? Because -4 plus 1 is -3, -4 minus 1 is -5, all right? So what Mr. Green must do is give an r sub x such that all values, an r sub x about c, which is 4, okay? Such that all of the x values correspond with y values in between -3 and -5, okay? And this is pretty easy to do. Let's say that he gives, I don't know, let's say that this is like 0.3. Okay, so let's say he says, okay, r sub x equals 0.3. So that means we're within 3.7 and 4.3. Okay, so that means that, let's say that this corresponds to 4.3 corresponds to this, and 3.7 corresponds to this. Well, look at all of these y values between are within, I'll use a highlighter here so you can really see it. So all of these y values between 3.7 and 4.3 are within -3 and -5. So far so good, okay? So far it's looking like the limit exists, but of course, Mr. Red is not fully convinced yet, so he wants to make it a little bit more difficult for Mr. Green. So he says, fine. What I'm going to do is I'm going to give you another r sub y, okay? And a much smaller r sub y to make it more difficult. So he says, all right, I'm going to give you an r sub y equals to 0.1, okay? So that means that we are between -4 plus 0.1, so that's like -3.9. Our y's are between -3.9 and minus 4.1, which would give us a -4, -4.1. Okay, so now what Mr. Green must do is give an r sub x such that all values lie within this narrow little gap, okay? And because, of course, this circle is much smaller, right? This is just a representative circle. But I think we can agree that Mr. Green can do that, right? He could take a really, really small r sub x. Let's say that r sub x is like 0.0001, all right? So he's going from pretty much, 0.001, which is, what's that going to be? 43.9999, right? Is less than x, is less than 4.0001. And although we can't see it, if we were to zoom in at this very little intersection, right, we get these little y values here. There would be a hole in the middle, of course, but all of these y values would lie between our -3.9 and -4.1, right? Well, blue highlighter over blue ink doesn't help. All right, so let's use that yellow, right? So the y values would lie between it. And the main idea is this debate could continue forever. Eventually, Mr. Red's going to give up and say, okay, yeah, you're right, Mr. Green. The limit does exist. But the idea is Mr. Red will give a smaller and smaller y gap. Mr. Green gives a smaller and smaller and smaller x gap. But the idea that all of these y values are going to be between, all of these y values that correspond to the x values will be between the gap that Mr. Red has given to Mr. Green, okay? So let's look now at a limit that does not exist, and I think this will make even more sense, all right? So let's talk about this one, for example. What is going to be Mr. Green's claim? Mr. Green claims that the limit as x approaches 7 of f of x equals 2, let's put some numbers here, 1, 2, 3, 4, 5. Mr. Green claims the limit as x approaches 7 of f of x equals to 3. Let's say that that's his claim. So what I'm going to do here is I'm going to show you one situation where Mr. Green can give an r sub x, and then a second situation where Mr. Green cannot give an r sub x. Therefore, we know that the limit does not exist, because the definition does not hold true. All right? So Let's do one where Mr. Green wins. Let's say that Mr. Red says, okay, I'm going to let my r sub y equal to 2. Okay, so that means we're going between 1, right? 3 minus 2 is 1. 3 plus 2 is 5. So we're going between this. Not too hard. Mr. Green says, okay, I'm going to let r sub x equal to, I don't know, 0. It could even be like 0.5, right? So if we're between 0.5, then we're going from 6.5 to 7.5, right? And we can see that all of these y values between 6.5 and 7.5, all of the y values correspond to values that are between 1 and 5, okay? Even though it's not continuous, so far so good. So far, it's looking like the limit definition is going to hold true. But that's because Mr. Red gave a big number for r sub y. Now let's give a smaller number for r sub y. Let's say that Mr. Red gives r sub y equal to 0.5. Okay, let me erase all of this. So now when Mr. Red gives a value for 0.5, let's take a look at where we are. All right, so we are between 3 minus 0.5, which is 2.5, 3 plus 0.5, which is 3.5. Okay, so now Mr. Green needs to give an r sub x such that all x values correspond with y values within that gap. All right, so let's say he's like, okay, I know this is going to be difficult. Let me try a really small one. R sub x equals 0.1. And that means that he's going from like 6.9 to 7.1. All right. On the right side, you're going to be okay, right? So from 7 to 7.1, we're corresponding with these values. And that's not a problem, right? That's these values here. The problem is from 6.9 to 7. 6.9 to 7 corresponds with these y values. These y values lie from, I don't know, 1.9 to 2, which are outside of this r sub y. Therefore, the limit definition fails. So the limit does not exist. All right? So I hope that made sense. Let me say that one more time. These values, all of the values here, all of these y values lie outside of r sub y, which is 0.5. Therefore, the limit fails, okay? So now let me explain, now that you kind of understand what's going on, let me explain all of this, the entire definition, okay? So, back to where we were at. So now we understand a little bit about what's going on here with the r sub x, the r sub y. So the statement, the limit as x approaches c of f of x equals L, okay, means that for every r sub y greater than 0, any r sub y that Mr. Red wants to give, Mr. Green can always give an r sub x such that if, okay, this line is a little bit difficult to understand. What it means is what I just said. If the x values lie within r sub x, then the y values will lie within r sub y. All right, so let me explain this a little more. So let me just, let's ignore the 0 for just a moment. Let's just talk about the absolute value of x minus c less than r sub x. So remember, what if I say that the absolute value of 3 is less than x? What does that mean, right? I'm sorry. What if I say the absolute value of x is less than 3, right? What does that mean? Well, x could be 1, 2, and 3. X can also be negative 1, negative 2, and well, it can't be negative 3, right? Because it's not equal to. But so what you can do is you can redefine the absolute value of x to be less than 3 to be negative 3 less than x less than 3. Okay? For any x's between negative 3 and 3, this will still hold true. So we can do the same thing here. The absolute value of x minus c is less than r sub x. That means x minus c is between r sub x and negative r sub x. All right? And adding c to both sides, we would get negative r sub x plus c less than x less than r sub x plus c. So our x lies between these values, negative r sub x plus c, which is just c minus r sub x plus c, which is c plus r sub x, okay? And now the reason that they include this 0 is because you can have a hole there. This would be the case where x would actually equal to c. All right, I hope that kind of makes sense. I think you'll understand it more when I get into the actual final formal definition of the limit, where it says except possibly at x equals c. Okay, so that's the reason that you have the 0 here. Okay. All right, so then the absolute value of f of x minus L is less than r sub y. So exactly what I just said, the same idea here. The absolute value of x less than 3. Let me change colors. So that essentially just means that f of x minus L is between r sub y and negative r sub y. Adding an L, okay, we're going to get L minus r sub y less than f of x less than L plus r sub y, okay? So what does all of this say? I'm going to show you on the next slide. I made this a little bit neater, okay? So this just essentially says that the statement, the limit as x approaches c of f of x equals L, means that for every r sub y greater than 0, there exists an r sub x greater than 0, such that if x lies in the interval c minus r sub x to c plus of r sub x, except possibly at c, could be a hole, then f of x will definitely lie between L minus r sub y and L plus r sub y. Okay? So just to show you, technically I should write it like this, right? C minus r sub x to c. X lies between c minus r sub x and c, and c to c plus r sub x, if I want to be, 100% mathematically correct here. All right, if x lies in this interval, then the f of x will lie within the r sub y. Okay? So now let me show you a little more about the complete definition here of everything. So this is what it says. This is the complete definition like you're going to read in a book. So let f be a function defined on an open interval containing c, except possibly at c, which is what I just said, because it can be a hole, okay? And let L be a real number, and the reason they say that is sometimes L can be infinity, but this won't hold true when it's infinity, okay? Infinity is not a real number. So if L is a real number, then we can definitely say the statement, the limit x approaches c of f of x equals L, means that for any r sub y greater than 0, Mr. Red can give any r sub y he wants greater than 0. Mr. Green can always give an r sub x greater than 0, such that if all the x lie in the interval c minus r sub x, c plus r sub x, except at c, then we know that f of x will lie between L minus r sub y and L plus r sub y. Okay? So now, plugging back in, I'm going to replace the r sub y with the epsilon, okay? I'm going to replace all r sub y's with epsilon. I'm going to replace all r sub x's with the deltas, okay? Even in all of these places, everywhere, I'll replace it. Same thing. I'm just replacing epsilon and delta, and now we have the complete mathematical definition of the limit, and it says that let f be a function defined on an open interval containing c, except possibly at c, and let L be a real number. The statement, the limit as x approaches c f of x equals L, means that for any epsilon greater than 0, so Mr. Red can give any epsilon he wants greater than 0, Mr. Green will always give a delta greater than 0, such that all the x's that lie within delta of c will correspond with y values that lie within epsilon of L. Okay? And that is the complete mathematical definition of the limit. All right, I hope that made sense to you. And yeah, so definitely work a couple practice problems on this to continue to develop this a little more. Now, this isn't super important to most students of calculus. This is more of something, if you're interested in studying mathematics, then you definitely want to get in the habit of understanding how to explain these in a mathematically precise way. So what this is a mathematically precise way to define a limit. All right? So that's all for this video. Thanks a lot for watching, and I hope this made your understanding of limits, especially the epsilon delta definition of the limit, much easier. All right, have a great day, and I hope you tune in for the next one. Bye-bye.